Welcome back to the Causal Inference seminar. Today, we're excited to have Anish Agarwal from Columbia University, who will talk to us about causal inference with temporal and spatial spillovers in panel data. After that, we will have an open format discussion with Iavor from Harvard and Ashesh from MIT. We're excited about this. Questions today will be handled by Jingwan. So maybe Jingwan, you want to say a few words?
Yes, I'm happy to. So we have two discussants today, but we're adopting the new format, which means that it would really just be an open discussion with contributions from our two invited discussants, but also perhaps from some of you in the audience. You're welcome to submit questions using the Q&A box at the bottom of your screen. And I'll bring them up to Anish at suitable times, and maybe we can all have a discussion about some really interesting questions at the end as well. Without further ado, I'll give the mic to Anish.
Hi, everyone. Let me share my screen. All right, is that working?
Yep, looks great.
Okay, great. Thank you again for inviting me back, the OSCIS organizers, and thank you, Ashesh and Iavor, for being here. My friend and collaborator Vasilis is also a panelist, so you can also ask him questions along the way. So my talk today is called on causal inference with temporal and spatial spillovers in panel data. So let me explain what that means. So panel data is a setting essentially where you're collecting, simultaneously collecting data of n units. The units could be, say, different geographic locations. It could be individuals. It could be stores, etc., depending on the context, over t time steps, right? So it's a time series. And they're undergoing different sequences of a possible interventions, right? So at any point in time, every unit can get one of a possible interventions. If you want to think about it visually, this is the way I think about it, is that you have one matrix, which is your observed outcomes, which is y, right? So y11 is the outcome for unit 1 at time step 1. Y and t is the outcome for unit n at time step t. Okay, so this is the matrix you're collecting of the observed outcomes. And you also have another matrix, which is the treatment assignment pattern. So you have the treatment assignment pattern is given by the variable a. So a11 is the intervention that unit 1 gets time step 1. A and t is the intervention that unit n gets at time step t. Okay, and the question we're going to be trying to explore in this talk is, how do we exploit structure across units, time, and assignment patterns for very personalized counterfactual analysis despite temporal and spatial spillovers? And now I'll explain what temporal and spatial spillovers means. So here's a motivating example from e-commerce. I spent the past year at Amazon. So suppose you're showing customers ads in an e-commerce platform every time they go on a landing page. So say you have Bob and Alice. So Bob gets the usual landing page when you go on a e-commerce website, and Alice gets a different version of it. So they have different ads, different rendering of the way the homepage looks like, et cetera, et cetera. Okay, that's on day 1. And day 2, say now Bob gets treated. He gets the new fancy web page, and Alice goes back to the original one. Okay. Now, say the purchase decision for any user on day 2 is likely to be a function of a few things. The first would be, say, the ads that were shown to the user on day 2, right? So the ads that were shown to Bob on day 2. There's probably also going to be a function of the ads that were shown to Bob on day 1 and the purchase decision of Bob on day 1, right? So if there are certain ads that were shown on day 1, you might have a memory, and that might affect what you do on day 2. And what you purchased on day 1 will also affect what you do on day 2. And that's what I call temporal spillover, where things in the past affect your current outcomes. Okay? Now, the second thing is that maybe Alice and Bob are friends, and they talk about what they like and what they don't like. And as a result, they influence each other's decisions making, right? So the ads that Alice was shown might affect what happens to Bob, right? And so that's what I call spatial spillover, when the people around you are affecting your outcomes. Okay, and then it could even be the case where the ads shown in the purchase decision of the user's social network on day 1 are affecting your outcomes today. And so that's what I call when you have temporal and spatial spillovers together. Okay. And so today's talk is really going to be about the identification of potential outcomes. Yeah, go ahead.
Well, you said we can ask questions. Just a quick one in the beginning when you were listening. Are you also considering the case if, for example, I have the advertisement and I purchase something and that product is no longer available for person 2? So that's slightly different spillovers, but it could happen in this situation. Is that something that you're also going to think about? Because I imagine that's like a fifth point here.
Yeah, that's a great point. I think, at least at a first pass, trying to think about it at the top of my head, I don't think we'd be able to consider that setting where, no, I don't think where there's that strong substitution effects. I don't think we'll consider it, but maybe there's an extension of it that will come to me eventually, but not immediately. So, so just to repeat, temporal spillovers are the setting where for a given unit, your past interventions and affect your current outcomes. So Bob got treated and then untreated, and then or treated and then treated. That has different outcomes on day 2. And then the spatial spillovers is for a given unit, the interventions of other units can affect your current outcomes. Okay. And this work on temporal spillovers, it's called synthetic blip effects. This is work with Vasilis, who's at Stanford in the operations research department there. And the spatial spillovers work is called network synthetic interventions, and that's with joint work with Sarah and Devrat, who are at MIT in EECS, and Christina, who's at Cornell Operations Research. Okay. And the focus of this talk is really going to be about the identification idea and how do you actually identify these potential outcomes. I won't talk much about estimation and inference. The estimation and inference results for the network synthetic interventions paper are in the paper. The synthetic blip effects, we're working on it. It should be in a revision soon. But I want to get to the heart of it, to me, which is the identification argument. Okay, so let's start with synthetic blip effects. So here, what is the outcome of interest? The outcome of interest is, I'll explain what the expectation is with respect to in a few slides, but it's a potential outcome for any given unit n at time step t under any sequence of interventions A1 to AT, okay? So in total, and in this setting, the potential outcome is only a function of the sequence of interventions you got in the past. It's not a function of what anyone else got. So in this part of the talk, I'll only be talking about temporal spillovers and not spatial spillovers. And I'll discuss how you can combine both of them at the end of the talk. Okay. So in this setting, the total number of causal parameters you have is going to be n, because they're n people, and a to the power of t. Okay, so let's just say it's up and down. Let's say it's 2 interventions. So it's 2 to the power of t times n. Because at any point in time, you have 2 possibilities for interventions, and you have t time steps, so it gets 2 to the t or a to the t more generally. Okay. And so now going back to the original question we started with this talk is how do you exploit structure across units, time, and assignment patterns to identify these potential outcomes? One way that's been quite popular in the literature and is really useful is something called latent factor models. Okay. So here are some examples of latent factor models that have been studied in the past that do not consider temporal and spatial spillovers. So here's a classic one. So here is YNT 0. So that's the potential outcome for unit n at time step t under control. Okay. And the assumption that's put is that it can be written as an inner product between Vn Wt plus a residual term called epsilon Nt. Okay. So Vn is the unit specific low dimensional latent factor. Wt is a time specific low dimensional latent factor. And epsilon Nt is the residual term. The additional assumption that's made is that this residual term is an independent random variable where its expectation condition latent factors is 0. Okay, and this epsilon is indeed what the expectation is going to be respect to for the purpose of this talk. And the nice thing about these latent factor models is they allow the latent factors to be confounders. And we'll allow for that as well, plus more. Okay, so this is fundamentally the assumption is that there's some low dimensional representation of what defines a unit given by Vn, and what defines a time given by Wt, okay? And you have this bilinear inner product between them that gives you the expectation of the potential outcome. Okay, so some latent factor models have been analyzed in the literature and are very popular. One is called synthetic controls. That was by Alberto Abadi, who was one of my advisors at MIT and his co-authors. And the latent factor model they study, it looks something like this, where you have YNT 0, it's equal to this Vn, comma Wt 0 plus its residual term. Okay, and this is the type of treatment assignment pattern they look at, where for some period of time, everyone is under control. Then some subset of units remain under control, another subset of units get treated. Okay, so capital A is going to represent the treatment assignment pattern for the units that actually got treated. Okay, and the question of interest in synthetic controls is what if a treated unit had remained under control? So the question is the treatment effect on the treated. Another model that I've studied with some of my co-authors, Devrat, another advisor of mine, and Dennis Shen, who's now at USC, is that they look something like this. So now we add more structure to the latent factor model. So we say the potential outcome for unit n at time step t under intervention A, not just under control, is given as follows. You have Vn and Wta. Okay. The key difference now is that in the synthetic controls world, you have this latent factor model is only on potential outcomes under control. right? Because the goal is to answer questions of what happened to a unit under control. In synthetic interventions, now I want to ask questions of the form, what happens to a unit that undergoes intervention as well? And so now you have to put more structure in the potential outcomes, in particular that there's the same latent factor that holds across all interventions, okay? And the type of treatment assignment patterns we studied look something like this, where everyone is under control for a while, and then some subset of units remain under control, some subset of units get intervention 1, 2, and so on and so forth, okay? You can see the big difference is that there's the WT0 on the left and there's WTA on the right. So essentially the VN remains constant in the synthetic interventions latent factor model across these different interventions. Okay. So the key idea, the intuition for identification is in this world of synthetic controls and synthetic interventions is that you can represent these unit-specific latent factors as linear or convex combinations of each other. So in synthetic controls, it's traditionally that you can represent them as convex combinations of each other. In synthetic interventions, we allow them to be linear combinations. But the fundamental idea is you can represent one unit latent factor as some combination of other people's latent factors. Okay. So what that allows for in the synthetic controls world is that you can express the expected potential outcomes of a treated unit as some linear combination of untreated units, or convex combination more classically. And because you have this additional structure in the synthetic interventions world, where this potential outcome, this latent factor model holds over the different interventions, you can now express the expected potential outcome of an untreated unit as a linear combination of treated units, because the VN is going to be uniform across the different interventions. Okay. But the basic idea is because you can represent these latent factor models as linear combinations of each other, you could represent potential outcomes as linear combinations of each other as well in expectation. Okay. That's the key idea to these kind of matching style estimators. Okay. So the question is, given this kind of intuition of latent factor models, can we naively extend these latent factor models to the case for the temporal spillovers? Okay. So let's think about a naive extension of the latent factor models that was previously studied. So in synthetic interventions, we had something like this, where Y and T is given this form. Now, let's say we're doing synthetic interventions with temporal spillovers, right? So now your potential outcome at time step T is not only a function of the intervention you get at time step T, but the history of interventions you get. One naive extension you could think of is that now let me make the latent factor model associated with time and intervention more complex, right? So now it's not only going to be a function of the intervention you get at time step T, but the entire sequence of interventions, right? So it's WT and then A1 to AT, okay? Now, what is the problem by if you try to naively extend it this way? Here are some limitations you will immediately run into. So let's say I want to estimate all parameters, which is all a to the power T times n parameters. It requires the sample size, the number of donor units you have, to scale exponentially in T. Okay? It requires some number of units to go through every sequence of interventions, and there's a to the T possibilities. So even with small t, you're going to run into sample complexity issues. And fundamentally, you can only identify intervention sequences you see in the data, right? But if there's a to the T possibilities, you're not going to see every sequence in the data. The second problem is that when you're dealing with this kind of data, you would like some level of adaptivity. So the intervention you get at some point should be a function of the observed sequence of outcomes you have. But if you try to naively extend these kind of latent factor models that were studied in, say, synthetic interventions, synthetic controls, you cannot have an adaptive intervention assignment pattern. And here's a DAG that kind of represents that. Fundamentally, the YN, which is the observed outcomes, don't have an arrow pointing into the ANs, right? And as a result, there's no adaptivity. The latent factor models can affect the sequence of interventions, but the observed outcomes cannot, right? And so that's a problem that we want to also overcome, is the sample complexity issue and the adaptivity issue. Okay. And so what we're going to study in this first part of the talk is, can we overcome these limitations by adding more structure to the latent factor models? So what if we add more structure? Two models that we explore in this paper. One is what I call an additive time varying latent factor model that looks something like this. I'm going to run through this slowly now and parse it. So your Y and T under the sequence of interventions A1 to AT has this particular form. The first thing to note is there's a latent factorization into a separable unit latent factor and a separable intervention latent factor. Okay, so the key thing is that the latent factor for N and the latent factor for A are separated. Okay. The second thing is that the effect of an intervention at any time step is additive on the eventual potential outcome, right? So if you look at this, it's a summation of WA, let's say L goes from 1 to T, of WA1, WA2, WAT, but they enter into the potential outcome function in an additive way. Okay, and that's going to be key to, that's kind of in some sense be the key structural assumption we make, and will motivate when and why this shows up. Okay. The third thing is the residual is a mean zero independent random variable conditional latent factors, and this is indeed what the expectation is going to be with respect to. And the nice thing here, why we call it time varying latent factor model, is because the effect, right, can be a function of the horizon capital T and the time period L the intervention is applied on. So you see T comma L, right? So the effect of the intervention at time step L, right, which is given by WAL, can be modulated by capital T and comma L. The second model we'll study is something called an additive time invariant latent factor model, where the effect is now only a function of the lag T minus L versus the double index T comma L. Okay, so when it's a time invariant latent factor model, the effect at a particular time only is a function of the lag between that time and the eventual horizon you care about. Versus in the time varying latent factor model, it actually depends on that specific time index. Okay. Any questions? Maybe I'll stop here for a second. Any questions?
Yeah, maybe just a couple of quick ones. The first one is, what assumptions are you making on the interventions? Because I got confused a little bit, which was in the synthetic controls, you're typically assuming the intervention is not random. And then in the second one, are you assuming that the intervention is randomized to some extent, or are you still in the observational study setting?
So it's in the observational study setting. So maybe I'll answer it here. So let me finish this question, and I'll try to come back to your question.
Perfect.
So,
and then my other question was, so maybe if you're going to come back to that, the other question is, a version of these models to some extent has been sort of studied in the biostatistics literature for a while, when you sort of assume that the treatment is additive. Can you tell us a little bit about those connections? Because I think those are really interesting, and maybe there's some differences, but it's been a while since I read. I know Jamie Robbins has like 100 papers on this.
Yeah, so this work, and I'll get to that in a second as well, in another 5 slides. So that's why this paper is called synthetic blip effects, because in some sense what we're doing is we're combining the ideas of these latent factor models with the blip effect literature, which is what comes from the biostat literature, and Robbins and Hernan being some of the people who've developed that thoroughly. And so again, I'll come back to the question in a few slides, if that's all right.
Okay, perfect. Yeah. I'm too eager.
No, please, that's fantastic. So this is the latent factor models we'll study, and I'll motivate why and how these latent factor models come up. But just as a TLDR of what we're going to achieve by having these additional structures. So if you have the naive extension of the latent factor model, the additive time varying latent factor model, and the additive time invariant latent factor model, what you get is that the unit sample complexity drops by adding the structure. So it goes from A to the T to A times T when you have an additive time varying latent factor model. And when you have an additive time invariant latent factor model, it actually, the dependence on T goes away, remarkably, at least to me. And the second thing is, as Iav asked, was what kind of interventions do you allow for? How adaptive can it be? How is it in the observational setting, in the randomized setting? So if you do the naive extension of the latent factor model and say synthetic interventions or synthetic controls, it's non-adaptive. So it can be a function of the latent factors, right? But once let's say some oracle could look at the latent factors, after that they have to decide the intervention policy, and that's it. In the additive time varying latent factor model, it can be adaptive after some time period. So there's some part where it's non-adaptive, it can be dependent on latent factor models, but it's non-adaptive to the observed outcomes. And after a while, it can become adaptive. And for the additive time invariant latent factor model, when you have the most structure, it can be adaptive after time step 1. So essentially, you can be adaptive right from the start. Okay, so that's in some sense, if there's one slide you should take from this talk, this is it.
Anish, could I just a quick clarifying question? So when you're talking about the unit sample size complexity, this is for recovering the latent factors. So what exactly is the sample complexity for?
Yeah, this is to recover the potential outcome for any unit under any sequence of interventions. So not the latent factors. So we're not identifying the latent factors themselves. We're just imposing that structure exists in a latent sense and implicitly. And this is to recover the outcomes for any unit under any sequence of interventions. One parameter I'm hiding here is the dimension of the latent factors, which we're going to just assume to be a constant. So here I'm just showing the dependence in A and T. Great. And in terms of adaptivity, here's one way of thinking about it. So in the time varying latent factor model, right, after some point in time, so there's a non-adaptive period where the outcomes are not affecting the interventions, and after some time period, the outcomes can start affecting the interventions. Okay. And in the additive time invariant latent factor model, they can start affecting the interventions after the first time step. Okay. So hopefully, yeah, this answers your question to some extent. Now, the question is, what motivates these additive latent factor models? We had this latent factor model put out here. What motivates it? The first one actually is an autoregressive process. So imagine you had the following autoregressive process that people study in time series literature and econometrics, in stats all the time, which is that, say, your outcome today is some linear combination of the previous outcomes and some linear combination of the previous interventions plus some noise term. Okay. That turns out can be expressed in terms, is a special case of an additive time varying latent factor model. And fundamentally, what's happening is those linear coefficients that hit both the interventions and the outcomes, those are what become, some combination of them become the VNTs. Those become the latent time-specific latent factors, okay? And then the noise, the ETAs, those basically get put into the epsilon term, okay? And the key idea of representing this way is that you recursively write the linear combinations. The outcomes really, if you think about it, are just additive sums of the interventions. Right, so if you keep recursively peeling the y ends and write them in terms of interventions, you will get that at any time point, you can write them as an additive sum of all the various interventions that happened. Okay? And that's really the idea of how this works out. Another model that's even more general in autoregressive processes is linear dynamical systems. Right, so it's like a state space model. So here, the transition matrices that you have, the A's and the C's and the B's and the D's, those are the things that go into the latent factors. Okay. And that's fundamentally what drives it. Again, the key thing in both a linear dynamical system and an autoregressive process is the effect of an intervention at any time step affects the eventual outcome in an additive way. Okay, so anytime that you have a setting where your intervention at any point in time has an effect on the eventual outcome in an additive way, you can probably write it in terms of a linear time varying or time invariant latent factor model. Okay, and the key thing we're saying in some sense is that these transition matrices that you have all have some structure. For these different, let's say, heterogeneous dynamical systems, they can all be written as some linear combinations of each other, the various transition matrices. So they all come from some sort of low-ranked manifold. And that's really what allows us to share information across these different dynamical systems or autoregressive processes. Okay, and linear dynamical systems are something that people study all the time. I study them, in electrical engineering for like control systems, signal processing. People study them in system biology. But it's a really neat way of thinking about a dynamical system. And even if you have a nonlinear dynamical system, what people tend to do is that if you sample your data quick enough, then they approximate it by linear dynamical system for short periods of time. It's a very useful abstraction in practice. Okay, so now let me go to the identification strategy for time varying latent factor models. Okay, so here's the assumption we make on the treatment assignment matrix. Remember, there's two things. So there's the potential outcomes matrix, or the observed outcomes matrix, and the treatment assignment matrix. We made an add structure in both places. So this is the structure visually that we put on the treatment assignment matrix. In particular, there's a staggered adoption into an adaptive regime. Can I explain what that means? So what we require of the treatment assignment matrix is that there's some control sequence, 0, 1 to 0, t, that is common across these different units. And the meaning of control can vary over time. And the units leave this control sequence in a staggered manner. Okay, so imagine like I'm a digital platform, I'm going through the regular status quo, and after some time, I get in a staggered way put into an adaptive regime. Okay, and the intervention assignment after leaving the control sequence can be adaptive to the data. And fourth, the assumption is that there's some subset of units that leave the control sequence at every time step. Right? So that's why it's a staggered adoption into this adaptive regime. Any questions about this? Sure, yeah, that makes sense. Okay.
So here, there's this, are you assuming that once you go into the adoption, you have to stick with
it? I mean, the adaptive regime can contain the control sequence. That's totally fine. So
can you just tell us a little bit, what exactly does that adaptive regime mean?
Adaptive means that now your outcome is your intervention is a function of the observed outcomes.
I see. So you can go from 0, you can go to the treatment, and then you can go back to 0.
Yeah. Though you can absolutely do that. The main thing is that going back to 0 after the adaptive regime can be a function of the previous outcomes. If you're in the control sequence, you decide that a priori, and then you stick with that.
I see. Okay.
But yeah, that's a great question. You can be going from intervention to control to intervention to control. It's just about how adaptive is that the person deciding the policy. Okay, so this is the treatment assignment pattern part. And now comes to, I think, your second question here, which you guessed well. It was that the second part of the identification strategy is using this idea of blip effects, which we'll go into, which was introduced by Robbins in '97 and further analyzed. I mean, there's a whole variety of papers on it by Hernana and Robbins. So the key idea we're going to be using is that we can represent the potential outcomes in terms of blip effects and baselines. Okay, so from now on, just for simplicity, I'm going to deal with the case where t equals to 2. It easily generalizes to general t. Okay, so the first thing is you write your potential outcome. So we're going to be dealing with the case of identifying the potential outcome for unit n for some intervention sequence A1 and A2 that is not observed runtime. Okay, we're going to write this potential outcome y and A1, A2 in terms of a telescoping sum. Okay, so yn A1, A2 minus yn 0, 1, A2, yn 0, 1, A2 minus yn 0, 1, 0, 2, and so on and so forth. Okay. The first thing is going to be called the blip effect for time step 1 with intervention A1. The second one is the blip effect at time step 2 and intervention A2. And then the last thing is called the baseline outcome. And I'll explain what these things are. Okay, so, but the basic idea is that to identify the potential outcome of interest, it suffices to identify 2 blip effects and a baseline outcome. Okay. So what's a blip effect? So blip effect at time step t for intervention AT is essentially the treatment effect of intervention AT compared to a baseline 0t for time step t, with common interventions for all other time steps. Okay, so if you were, let's say in engineering, we also call this an impulse response, which is what happens if I just tried the intervention at a particular time step and the rest of it will say it was under control or something. Okay, so you're trying to learn the effect of the intervention at that particular point in time. Okay, that's what a blip effect is. Okay, and the baseline outcome is really the question of what the potential outcome of a unit remain under control for all t time steps. Okay. So how does this latent factor model connect with these blip effects? So we had this structure for the additive time varying latent factor model. Here I'm dropping the dependence on 2, right? So normally it should be 2 comma L, but I'm depressing the dependence on 2 for notational simplicity, right? So we said that to represent the potential outcome, it suffices to identify the 2 blip effects and the baseline outcomes. If you have such a latent factor model, what it implies is that the blip effect also has a latent factor model representation given as follows. Okay. So another interpretation of what we're doing is that we're making a latent factor model assumption on the blip effects, which is the key object of study in the biostats literature for dynamic treatment effects. Okay. And so the fundamental idea we have in latent factor models is that we can represent the latent factors in terms of linear combinations of each other, and that lets you represent the outcomes as linear combinations of each other. The idea here now is that we can represent the blip effects and the baseline outcomes as linear combinations of each other. And that's going to be the key, the heart of the identification strategy. Okay. So one way of thinking about what we're doing is we're trying to bridge this literature of synthetic controls and interventions, the latent factor model literature, with the blip effect literature. And that's fundamentally what this paper is about. Okay, so now I'll give you an idea of the proof of how it works. Okay, so we had this telescoping sum. We're going to identify blip effect at time step 1, blip effect at time step 2, and the baseline outcome. Here's how it works. At step 1, you identify the baseline outcome. Okay, and the idea is very much, it's essentially the synthetic controls idea. So you look at all the units that received the observed outcomes, the exact control sequence, 0, 1, 0, 2. Those are the donor units in this particular setting. Okay, and then because you already observed those outcomes for them, you have the baseline for these donor units. Okay, then by the latent factor model that we have, we can create a synthetic baseline or a synthetic control for every unit as some linear combination of the observed outcomes for these control units. Okay, so it's basically synthetic controls. You look at the people who get control, you write everyone else as some linear combination of them, you have a synthetic baseline for every unit. Okay, so that's step 1. So once you've done step 1, you now have a baseline for every unit estimated. Okay. So that first part's done. Now step 2 is I want to identify the blip effect times step 2. So that's the blip effect at the final time step for where here at this point it's 2. Okay, so I want to identify the blip effect at time step 2 for intervention A2. What you do is you look at the unit that received 0, 1 in the first time step and received A2 in the second time step. Okay. Now I want to somehow tease out the blip effect at just time step 2. The nice thing is if I subtract the baseline from them, which I have from the first step, that exactly equals the blip effect for these units at time step 2. Okay, so I look at the people who get intervention 0, 1, then A2. I take the outcomes, I subtract the synthetic controls for them, and I now exactly have the blip effect for them at time step 2. Okay. Now, if you use your latent factor model trick again, now you have a synthetic blip effect for every unit for time step 2 under intervention A2. Okay. So, and you can repeat this process now for every intervention. So you don't just do this for A2, but do this for every possible intervention in the second time step. And so now you'll actually have a blip effect at time step 2 under every intervention for every unit, okay, by just repeating this process a sufficient number of times. Okay. I think there's a question in the Q&A. Should we do it later or now? I'm happy to do it either way.
We can do it now. It's a question from Thomas Richardson. It's a comment on the Robbins model on the blip effect, which do not assume control before time t. In other words, I think what Thomas meant was when you look at your blip for A2, he's saying the Robbins model assume you take this natural realization of A1 instead of fixing it at 0. So the question was, do the blips here take 0 prior to the time of the blip?
That's a great question. So in our setting, we will be only looking at the people. The blip effect, given the latent factor model, only depends on the intervention you get at that time step. It can be any sequence of interventions in the other time steps, as long as it's common between you and between the interventions you got and the counterfactual. But because it's the latent factor model, it only depends on the intervention at that time step. But for the identification strategy, we will be looking at people who got the control in the time step before. Okay, so for this specific identification strategy, we'll be looking for identifying blip effect 2, we'll be looking at people who got 0, 1 in the first time step.
Maybe a natural follow-up to that. I guess you may have different ways to decompose this effect. For example, you can use 1, 1 as the baseline outcome, and you have another telescoping sum. So Absolutely. That would be a different identification strategy. Would that matter for your method?
I think it would generalize in a straightforward way. So if you can just redefine in terms of which interventions you're looking at, but then the donor sequence, the units that you can consider control will now be the 1, 1 sequence. And you could repeat the process in the same way. So I think it just depends on correctly defining the control, which units you use in the donor group at which time point.
Okay, thanks. I think Thomas just added a comment that I think he said, I guess the meaning of blip has changed.
Yeah, so just to repeat once more, maybe, it's a good point. So here what I'm saying is the blip effect at time step AT compared to a baseline, right, with common interventions at all of the time steps. But because of the latent factor model we assume, it's only a function of the intervention you get at the Tth time step. It's not really a function of what happens at the other time step because they cancel out, because we assume that the effect at any time step is additive. So as a result, you can have multiple definitions of the blip effect at a particular time step. But I think maybe I'll talk about that offline.
Yeah, that's very, very helpful. Thank you.
Yeah. Okay, so we said if you do this step now, where you take the outcomes of people who get intervention A2, you subtract the synthetic baseline, you now have the blip effect isolated for them at time step 2. Okay. And now say I want to identify the blip effect at time step 1. Here's where it gets a little tricky. You have to use a bit of recursion. Okay. So what you do now is you look for the unit that received intervention A1 at time step 1. Okay. Now they received some intervention A2, capital A2 at time step 2. It could be anything. The nice thing is we now subtract the synthetic blip effect for them at time of A2. Okay. And A2 is the observed outcome for this donor unit. The nice thing is in step 2, we'd already identified this blip effect. So we can subtract it. we subtract the synthetic baseline, and that actually isolates the blip effect for these units. Okay, so let me do it again. So you look at the units received. I want to identify the blip effect at time step 1 for intervention A1. The right set of units that will be my donor group now will be the unit that received intervention A1 at time step 1. And let's say they received some intervention A2 at time step 2. What I'll do is I'm going to subtract two synthetic things now. I'm going to subtract the synthetic baseline, and I'm going to subtract the synthetic blip effect at time step 2 for the intervention that they actually got, like the actual intervention that they got. And we subtract these two things, you can easily see that the blip, what remains is the blip effect at time step 1 and the intervention A1. Okay. And again, using the latent factor model, you can now create the synthetic blip effect for all units via linear combination of the blip effects of these donor units. Okay, so here's where the recursion happens. Because to identify this, you need to identify the blip effect at time step 2, and that's something we'd already kind of stored in memory through this dynamic program that we ran. And so if you do this, you now have a blip effect for time step 1 identified under any intervention. And as we said, because the sum of these things give you the potential outcome of interest, you now have actually identified YN A1, A2. And that's fundamentally it, right? You can obviously extend this to T time steps and any sequence of interventions, but it's really this idea of where you identify the baseline first, and then you build out the effect at the last time step. Once you have that, you learn the blip effect for time step T minus 1. You have that, and you recursively build it out till the end. Okay? And that's basically the idea, is you keep using this latent factor model to learn these synthetic blip effects. Okay, and so that's really the idea for the additive time-varying latent factor model. And you can easily argue that given that kind of recursive strategy, the unit sample complexity now scales as A times T rather than A to the power of T. Okay, and there's a different variant of this argument that will work for the time-invariant latent factor model that actually only allows sample complexity just being A. Okay, and the fundamental difference is that in the time-varying latent factor model, we're only using the outcomes of the Tth time step. Okay. In the additive time-invariant latent factor model, you actually look at the outcomes of every unit, and you look at their sequence of outcomes. Right. So you're looking you're utilizing the data not just at the last time step, but over the entire sequence of trajectories, and that's really what allows you to bring down the sample complexity from A times T to A. But I'll leave those details for the paper. So
Anish,
a summary of the.
Can I ask you a quick clarifying question? Or as I should ask this earlier about what you mean by an adaptive policy. So does that, what you're assuming about the adaptive policy, should I be thinking of that as it's some version of sequential randomization conditional on these latent factors? Is there like an overlap assumption, or is it something weaker than that?
Yeah, so in the naive latent factor model, so in all of these models, you allow for there to be confounding based on the latent factors. Okay, so whether it's adaptive or non, when I say non-adaptive, I still mean that you can allow for it to be dependent on the latent factor model, on the latent factors. When I say adaptive, what I mean is now it can also be a function of the observed outcomes. Now, what does that mean? It means it can also be dependent on the noise that is introduced at every time step. So the epsilon that's introduced at every time step, that can also affect my treatment assignment pattern. And that's fundamentally what I mean by adaptive. Okay, so just to repeat, the latent factors can be affecting the intervention assignment in all these different models. So even in a non-adaptive setting, it can be a function of the latent factors. But the epsilon, which is what affects the observed outcomes, those affecting the treatment assignment pattern can only be in the adaptive regime.
Does that clarify? Sorry, Anish, there's a related question from the audience. The question is about whether you assume measurement invariance, which I think means if you assume there's an equal factor loadings, that doesn't change over time, if I understand the question correctly. Is that the assumption here?
So let me see if I can. I don't exactly know what that means, measurement invariance, but fundamentally, the model is something like this, right? So here, for example, the latent factor for the unit, right, is something that is changing for at capital T and L. So it's a different latent factor at every time step.
Right.
But when we say measurement invariance, I guess the invariance that I need is that the latent factor is not a function of the intervention. So that's the fundamental separability that I'm exploiting.
Okay. Yeah, let's move on.
Sounds good. So the summary of the key ideas is that idea one is that we have an additive time varying latent factor model, right? Which is motivated by autoregressive processes and linear dimensional systems. Idea two is that we rewrite the outcomes of the blip effects and baseline outcomes with this latent factorization. The third idea is that we identify the baseline outcomes using the synthetic controls approach. Right. And the fourth idea is that we use dynamic programming or recursion to recursively identify the synthetic blip effects for all the t-type steps. And these four things playing together is really what gives you identification. And with that, I'll end the temporal spillovers part of the talk. We'll come back to it at the end when I talk about when you have temporal and spatial spillovers together. And now I'll talk about spatial spillovers when you have network interference. It's called network synthetic interventions. So here the target causal parameter is, rather than being a function of the history of interventions, it's a function of the interventions that everyone else got as well. Okay, so it's YNT AI, where AI goes from 1 to n, which are the n different people. Okay, we'll make restrictions on the type of spatial spillovers we allow for in a second. And what the expectation is defined with respect to, I'll talk about in a second. And again, here we allow for spatial spillovers, but not temporal spillovers, because your potential outcome is not a function of the history of outcomes. Okay? So again, if there was arbitrary spillovers across all units, then sharing information becomes challenging. So you want to restrict the extent of the spatial spillovers. And what people do, and what we do as well, is that you assume there's some graph over the units. Okay, so here's so let's say here the nodes, which is the blue circle, so the units, and the edges defines between two units means that they're neighbors. Okay, so that means if there's an edge between, say, me and Ashesh, that means his intervention affects my outcomes. Okay, and if there's no edge between, say, me and Dominic, that means whatever happens to him, it doesn't affect my outcomes. And so say for this unit that is being pointed to, that outcomes of this unit is dependent on the interventions of its immediate neighborhood, which is circled in red. Okay. And so under this kind of assumption, the potential outcome becomes less complex. Rather than being a function of the interventions of all the n units, it's only a function of the neighborhood of n, which is given by mathcal n, comma n. Okay. So what is a latent factor model that makes sense with such a neighborhood-based spillover restriction? So this is the model in synthetic interventions. Here's the extension. So rather than just being Vn WTA, it's an additive sum of the Vn's for all your neighbors. Okay, so in some sense now it's a more complex latent factor model, where now it's essentially a latent factor specific to unit neighbor I and unit n. Okay, so now it's going to be basically a more complex model because it's an additive sum of the latent factors for me and the interventions I get, but also for the interventions my neighbors get. Okay. And the potential outcome function is a function of not just the interventions I get, but the interventions that my neighbors get as well. Okay. And the key assumption again is that the effect is additive over the different neighbors. Okay. Another way of looking at this is because you have this additive model, you can write this latent factor model in terms of this elongated latent factor. Okay, where this V tilde n is really you're concatenating the latent factors for you, the latent factor for you and your neighbor one, you and your neighbor two, and so on and so forth. You have this larger latent factor, and that's another way of representing what's happening. Okay. So here's a way of comparing it. So SI with spatial spillovers is essentially have this elongated latent factor model, right? And so it looks a lot like the synthetic interventions model, but it's this larger latent factor. It's a more complex latent factor model to deal with the neighborhood interference. Okay, that's really the latent factor model that we're studying in this literature. And so the key identification idea is that you simply change the donor group, right? That's really it, is that you just have a smaller donor group to choose from. So suppose we have the following graph with binary interventions. Okay, so the synthetic controls question would be, say, for this unit that was treated in red, like what would have happened to this unit under control? That's the question we ask in synthetic controls, right? And all the people in blue are valid donors for you, right? If you don't assume any sort of neighbor interference. The right question to ask of synthetic controls with neighbor interference is what would have happened if if the unit and my neighbors were under control. So for this particular unit, its neighbors would be the two next to it, one that's blue, one that's red. Okay. And the valid donor units given the model are the units that have the same number of neighbors as you. So for this unit, it has two neighbors, right? And I want to know what happens to it under control. So which of the units that have two neighbors, and such that all of the neighbors, its neighbors have control, it's these two. Okay, so these are the two that become the valid neighbors. Yeah, Dominic, you have a question?
I just wanted to remind you of the time. So in order to have some time for discussion. Okay, yeah.
Perfect. I'll be done in 5 minutes. Yeah.
Sounds great.
Okay, so the fundamental idea is that you just change the donor group rather than being anyone that gets under control. It's units that have the same number of neighbors, and the neighborhood of them have the target intervention assignment. Okay. And so with this kind of elongated latent factor model, the assumption is that the elongated latent factor model can be written as linear combinations of the valid donor group, right? So the valid donor group here are the units that receive have the same number of neighbors, and the target intervention assignment for themselves and the neighbors. And what that implies with the latent factor and the overlap assumption is that the expected potential outcome of the unit can be returned in terms of observed outcomes for those units, for the donor group units. Okay. And again, the idea here, it's not randomized, but you assume that condition on the latent factors, the assignment is independent of potential outcomes. So we don't allow for adaptivity. And that's fundamentally it, right? So the TLDR for the neighbor identification, the network synthetic interventions, at least for the identification part, is we have a more complex latent factor model. And algorithmically, what that means is you have a smaller donor group to choose from when you think about control. You have to be more selective, more careful when you think about what's a valid unit, and you think about the neighbors and the treatment assignment of the neighbors. Okay. So in conclusion, how do you simultaneously handle both temporal and spatial spillovers? So the idea of temporal spillovers is you have this additive latent factor models over time, and you recursively identify blip effects. For spatial spillovers, you have this elongated latent factor model, and you look at the neighborhood assignment. And I think the way you would potentially handle temporal and spatial spillovers together is you have this additive elongated latent factor model, and you essentially recursively identify network blip effects. And I think that would be one way of getting towards combining both of these things. This hasn't been done, but this is my conjecture of how one could do this. Okay. And with that, I'll end. I'll just give you something. I think latent factor models are super interesting, and there's a ton of work to be done here. I'll give you some of the things I've been thinking about. One is called synthetic combinations, which is with Abhinit and Suhas, or at Berkeley and MIT, where now we think about where the interventions are combinations, like a factorial design or permutations. And so how do you add structure across combinatorial interventions? Another work I'm doing with Alberto and Raz and Abhin, Raz at Cornell and Abhin at MIT, is doubly robust latent factor models, where you create doubly robust estimators by assuming the outcome matrix and the assignment matrix are low ranked, or either one of them is low ranked. Here's strategy proof decision making, where we combine it with ideas and mechanism design, where what happens if units actually manipulate their pre-intervention outcomes to get a better treatment assignment? How do you deal with those kinds of settings? Some work with Alberto and Devrath on formally bridging causal DAGs with latent factor models. Causal matrix completion, which is bringing some of these ideas to the traditional matrix completion literature with missing ordered random data. And some work I did with Rahul, who's now at Harvard, on bringing some of these ideas from latent factor models to deal with when your covariates have been corrupted with Laplacian noise to get differential privacy. Okay, and with that, I'll end. Thank you very much for your attention, and please, any questions we welcome.
Thanks for the very nice talk. So we're now going to switch over to discussion. So this will be a discussion between Yav, Ashesh, and Anish. Also, yeah, please, if you have any questions, submit them via Q&A so we can also bring them in during the discussion. Yeah, with that, I'm handing over to Yav and Ashesh.
Ashesh, you want to go first?
Oh, yeah, I guess, so one thing that'd be helpful for me to think about, at least in the first part of the talk on the synthetic blip effects, is, so if I start with sort of the estimand I'm interested in is average potential outcome along a particular sequence of treatments. There's sort of large work showing I can identify, causal estimands like that if I'm willing to make some sort of sequential randomization assumption, some sequential overlap, and then, do a sort of recursive identification strategy. So it'd be helpful to try to, for me, I was trying to, as you were going through it, trying to map back to sort of what sort of the latent factor model is buying me, and then potentially at what cost is it buying me those additional gains. So it seems like sort of the main benefit is it allows you to relax sequential randomization, because now I can think of these latent factors as like unit specific unobserved confounders, and I can still get point identification of sort of the causal estimate I'm interested in. And potentially the cost is I'm imposing more structure on potential outcomes through this latent factor model. Is that a reasonable characterization of like what you get here? And then if it is a reasonable characterization, do you have a sense of like how I should think about, is this latent factor model like quite restrictive? If it is, what is it ruling out? And if it is ruling out stuff, does it have any like testable implications in the data? Could we think about that?
Absolutely, that's a great question. So in terms of this question of overlap, I think of overlap as the analogous thing in the latent factor model world is that you can write a latent factor model for one unit as a linear combination of other units. Right, so that's the analogous of overlap, where the treatment assignment is diverse enough that people of one kind of latent factor model can be written as linear combinations of other people get other treatment assignments. And so that's where the diversity of the treatment assignment comes. So for example, if you have an adversarial treatment assignment where you look at the latent factors, you decide that people of one kind, I put them in treatment 1, and people who have an orthogonal set of latent factors, I put them in treatment 2, then you can write them in terms of each other. And I think that's how I think of at least the overlap assumption, to some extent, being the equivalent thing. Mm-hmm. The sequential randomization, I think the basic idea is that you have these, you don't have covariates anymore. You don't rely on these covariates and say, condition on these covariates, the treatment assignment is as good as random. You say instead that these low dimensional latent factors that give you that. I think the main thing that we're imposing, because I don't think the latent factor model itself is that much more restrictive than selection of observables, in my opinion. It's just saying that there's some low dimensional representation of these observables that is driving the assignment mechanism. I think the bigger assumption that's being made is that you have this additive time-varying latent factor model. And I think that's the main assumption being made. And the motivation that we took for that is because, well, one thing that people study a lot in the literature across a variety of literatures is autoregressive processes and linear dynamical systems, and that's an example. And so I think in terms of testable assumptions, there's a lot of work that's done on I think identifying whether you have an AR process that's driving a system or a linear dynamical system that's driving a system. And we haven't done this, but I think it would be great to see if one could port some of those tests to see whether you actually have at least one sided test of whether you have a latent factor model, an additive latent factor model or not. Mm-hmm. And the reason you don't need sequential randomization as much is, if you look at the identification argument, you're really only relying on the observed outcomes at, say, till you get into the adaptive period. So once you get into the adaptive period, I don't actually look at the outcomes anymore. So at that point, you can be as adaptive as you want, and no one's going to care. Alberto made a similar point, and think in the synthetic controls paper, is that for the units that get treated, I make no assumption about the treatment assignment pattern of what happens to them on the treatment, because they never look at that data, right? I only look at the data of the people who remain under control. And so that's the data I need to make an assumption over. So fundamentally, the assumption you need to make is only over the data you use. The data you don't use, it can be as arbitrary as you want.
Mm-hmm. So one thing I'm wondering is, how robust are these models? Because when I'm thinking of something like synthetic controls, it does a pretty decent job, even if some of those assumptions on the factor model are broken or violated. But here, because you're doing this recursiveness, I imagine they must be way more sensitive to this additive assumption, which frankly, I know you're saying maybe it's not that strong, but I was trying to imagine what are real applications in causal inference where I can truly trust this additive? Like healthcare, it's probably not necessarily additive. E-commerce, it's probably also not necessarily additive. There's probably some sort of U-shaped or something like that. So like how robust, have you done any sort of studies in terms of robustness here?
Yeah, so I think you're totally right that in terms of estimation, so one is about identification, at least in terms of estimation, there will be this exponential dependence on T that will show up if you want to estimate anything correctly. one thing that people do a lot in the literature is that you say it's not a function, your potential outcome today is not a function of the entire sequence of history, but let's say the past k time steps, right? And so then that's one way that if you're willing to make such an assumption, then it helps, because then you only need to identify these blip effects for the past k time steps.
Yeah.
And then potentially could use a test that people use for AR processes of how many lags you need. A similar type thing could potentially show up here. Sorry, but go ahead.
Well, my question was more about what if the additive assumption is wrong, right? Because I think that's really at the heart of this is you basically sort of traded some versions of non-parametric identification for parametric identification. And my question is, what if your model is wrong? And what I was saying is that in synthetic controls, like it feels like because you're not doing this recursive thing, you have a little bit more robustness. Whereas here, because you're doing this recursive thing, you're taking all these differences. I'm imagining if this additive assumption is even slightly violated, then things can go really, really wrong. And I'm just curious, do you have any thoughts on that?
I think but I think then, the with synthetic controls, with interventions, you're putting the assumption somewhere else, that you don't have these spillover effects, right? Sure. So it depends on where you want. I guess there's no free lunch, right? So if you want to allow for these temporal spillovers where the interventions in far back in the day can affect you, then a more stringent assumption is being placed. With something like synthetic controls, where your outcome today is only a function of the intervention today, you can get away with more. But I totally hear you on the question of, is there a way to relax this additive assumption to allow for, say, some level of nonlinearity, or say in some basis you have nonlinearity? It's a good question. I don't know the answer. One thing, I think the first immediate thing to do is that there's a lot of literature on testing for when you have a linear dynamical system or a regressive process, because that's a model we use all the time in finance and econometrics. So you can always use those. I think the first thing to do is to use those robustness checks and bring this to this literature. Because you can at least have a one-sided test of, okay, if you have an autoregressive process there, then you know that's a special case of this. I'm assuming less than an autoregressive process.
So there is a related question from the audience, which is, I think, coming from a different angle. This is from an anonymous attendee. So he or she said, my experience with using models to identify time-varying treatments is that it is quite data demanding, and bias reduction is often overweighed by variance increase, as far as Monte Carlo simulations have suggested. Can you tell us if your approach is more efficient or not than other approaches identifying average treatment effects in a dynamic setting?
That's a good question. We haven't done a systematic study with like the entire literature of how you would do this, different possibilities. What I have found is that when you have a latent factor model structure that is in your data, then exploiting it by regularizing your fit to just the low rank part of it tends to actually dramatically reduce the variance compared to approaches that don't explicitly exploit that low rank structure that exists in your data. Now, again, a lot of this work is for the setting of personalized counterfactual analysis. So another good question that I don't know the answer to is that if you create personalized counterfactual trajectories for everyone, and then you take an average treatment effect, is that better than directly just getting the average treatment effect? Maybe there's a better way of, maybe a less stringent latent factor model, or just a better way of doing it if your goal is just to estimate average treatment effects. I don't know the answer to that.
Great, thank you. I think we're like at 1 hour, so I'll just quickly wrap up, but if you have further discussion, feel free to have it afterwards. So first of all, yeah, thank you so much, everyone. First, Anish, for a very nice talk, but also to Ashesh and Iavor for a very interesting discussion. Thank you all for coming. Next time, we're going to have Maya Mathur from Stanford University, who will talk about the common cause principle for eliminating selection bias in causal estimates through covariate adjustment. Thank you all for coming. Hope you have a great week, and see you next time.
Thank you. Bye-bye.